Okay, the aim of this talk is to just offer new data, to experimental data to question the effect of hydrogen on intergranular fracture. Specifically, we focus my talk on nickel-based alloy. I would like to thank for this data Yasmine, in PhD student in La Rochelle University, and also Siva, which is a postdoctoral position. And to question that, we use two materials. There's a polycrystal nickel, pure nickel, and the second one is WASP alloy, is nickel-based alloy with aluminum, specifically, and titanium. And we question the effect of the slip mode, the planar slips of the wave slips. For nickel, we have a planar wavy slips, and for the WASP alloy, we have a planar slips because the share of the precipitate and use more localized deformation. Okay, for that, we first try to question two aspects: the effect of grain boundary character and their interaction with hydrogen to question intergranular fracture, and the precipitate state implication on intergranular fracture. And for that, we start by the damage in relation with the slip mode. And the second point is to question the effect of hydrogen on mechanical behavior. Use for that the Cox making model is a classical model. And then we try to question the fundamental process for hydrogen enrichment using intergranular and question specifically intergranular fracture. And we conclude on that. Firstly, for wavy slips, polycrystal nickel, we show that when you modify the strain rate, the ductility is not affected when you have no hydrogen in the material, and it's classical dimpled fracture. And if we added hydrogen, we have a loss of ductility, which depends on strain rate. And for large strain rate, the implication of hydrogen is not clearly. We have also a deeper fracture. But when we focus on the low strain rate, we have a large discrepancy of the ductility in relation with intergranular fracture. This fracture seems to be a cleavage, but it's not really the case. When we focus on the surface, the nice work of Martin showed in the past that we have a slip line, and we have many people who show the similar results now, which means that we have a contribution of the plasticity to the loss of ductility in relation with addition of hydrogen. The same work is obtained also for precipitate states. Here is a result for nickel alloys with gamma and gamma zone precipitate, and we have no effect of strain rate of the ductility when we have no hydrogen, when we have a large loss of ductility when we added hydrogen. In this case, we have only dimpled fracture with and without hydrogen, and we have, in this case, intergranular fracture with a slip line or slip band on the surface. And additionally, in this work, Simon in our group or Zhang group, we also show that we have a cavity, a nanovoid, which suppose that hydrogen in the grain boundary segregation produce a vacancy. And we have a nice work on the Zhang group on the numerical work, which demonstrates that. Okay, now if you try to question the implication of hydrogen on intergranular fracture for pure nickel, we try to question the nature, the character of the grain boundary. And we separate the grain boundary in two domains. The first one is a special grain boundary, is a CSL grain boundary, which is defined as a coincidence seat lattice lower than 29. And then the other family is random grain boundary with a higher value than this 29. And we have shown in the past, in PhD of Abdelali, that the diffusion coefficient increase when we increase the fraction of random grain boundary. We have a large measure orientation and large excess of the volume. And then it's a clear demonstration that this kind of grain boundary is a short circuit of diffusion. And the other class of material of grain boundary, is a coincidence seat lattice grain boundary, and is specific location for trap. The number of trap increase with a fraction of the CSL. And using the local approach also along the grain boundary, we use a TOF-SIMS analyzer and a BSD, and we show that we can check the profile of hydrogen when we cross a grain boundary. And we have two kinds of situation. we have a gap. When we close this ground boundary, we have a gap of the concentration of hydrogen, similar for the three kind of ground boundary. And in this case, we have a gradient of distribution of hydrogen along the ground boundary, which means that for the statistical approach of that, we have demonstrated that in the ground boundary, we have a gap, which means that when hydrogen arrives, it segregates on the ground boundary and diffuse along the ground boundary, is in accordance with the global macroscopic data. And for the CSL ground boundary, we show that mainly ground boundary is a trapping location. Hydrogen segregate on this place and it stayed on this place. Is why we identify a gradient of distribution of hydrogen. Then now the question is, what is the consequence of the evolution of the fraction of CSL on the fracture, intergranular fracture? For that, we perform different heat treatment in polycrystalline nickel, and with the same grain size, we modify the fraction of the CSL. Here is a low fraction of CSL than in this case. And we perform tensile test, and we show that when you added hydrogen, we have a loss of ductility in both cases. But the loss of ductility between which we compare the black dot and the green dot is important, is important in this case and lower in this case, which means that the fraction of CSL impacts the ductility, and we question that by the fractography analysis and also with elongation ratio. We use the elongation, the elongation ratio as the fraction of the elongation ratio obtained with hydrogen minus by the elongation without hydrogen. And this result is presented here. Firstly, we have checked the surface fracture and the intergranular fracture in both cases when we added hydrogen. And in this case, the ratio identifies effectively an hydrogen a factor which characterizes the hydrogen enrichment. And we show that this factor decreases when you added the concentration of hydrogen, but it depends on the fraction of CSL, and which means that we have two domains. The first domain when this ratio do not have a less evolution, but in this domain you have a large decrease. First, we question the first domain here, and when we decrease the fraction of CSL, which have a large hydrogen enrichment, increase the hydrogen enrichment, which means that we have directly a link of the fraction of CSL and the hydrogen enrichment. And if you focus on the surface and we zoom on the surface of the fracture, we see the emergence of a nice slip band, which means that hydrogen plasticity have a large contribution of that. Actually, we work on the second domain and we have just 1 point. This is life, it's all time. And the new point is here. And in this new point, in this domain, we have also a slip line, but also a small cavity, a small void, which is probably the production of nanovoid in accordance with the numerical work of the group. Now, if you focus on the West alloy and try to question the effect of the planar slips on the intergranular fracture, we have used West alloy and with gamma prime precipitate, spherical precipitate, and maintain the grain size and the fraction of CSL, and only modify the radius of the precipitate. It's like that. And the first result is interesting, is the fact that the lattice misfit between gamma and gamma prime evolved like that. We have the first ring increase of this misfit, and then a decrease and a stabilize of that. In second time, we try to evaluate a different domain of the interaction of dislocation with the precipitate. For that, we use the indentation, and then we evaluate the critical stress induced by the precipitate, and we have a nice evolution when we have an increase with the first domain of size of precipitate, small precipitate, and then a decrease and a stabilize. Use it 3 kind of model to describe that and define 3 domains. The first domain corresponds to the model we consider just an interaction of 1 dislocation with the precipitate, like the red curve. The second domain considers the interaction of 2 dislocations, the pair dislocation, and then we have a decrease of the shear stress necessary to shear the precipitate. And the last one is O1 precipitate interaction, which is bypassing by O1 process. And we have also evaluated, the coherence strengthening, but this value is very low than the other contribution, and it's negligible in this situation. Now, if you added hydrogen, 3 domain, we answer this 3 domain for the misfit evolution, increase of misfit, a decrease of misfit, and stabilization. And then we have measured the concentration of hydrogen with the same charging condition. And we show that when we increase the radius size of the precipitate, firstly is the blue dot, experimental data, we have an increase of the concentration of hydrogen. And then after the critical value, we have a decrease of that, the blue dot. To question that, we associate this behavior with elastic field around the precipitate and use a misfit to calculate hydrostatic stress around the precipitate, and then the hydrostatic stress, and then the excess of the solubility near the precipitate, and then we make a summation of that to evaluate the concentration of hydrogen due to the elastic field around the precipitate. And it's the red dot, and we show that we have an increase of this concentration, and we have a good results about that. But when we check the data for higher radius, we show that we have a discrepancy, probably due to the GND. And then we check that, we use a TDS, thermodescription spectroscopy, here for specific temperature rate, and show we have 4 peaks. And the second peak is directly linked to the elastic field around the precipitate, and the last one to the GND and also the dislocation in the grand boundary. And we show that when you increase the radius, we have firstly an increase of the concentration of around the elastic field, is a blue dot. But when you check a specific value of radius, the main concentration is linked to the deep trapping on GND around the dislocation. Then the results of the mechanical behavior is like that. For the first domain, we have an increase of the ductility when you have, okay, 3 minutes. We accelerate, sorry. We have 3 kinds of behavior. We have an increase of ductility with hydrogen and a softening. In the second domain, we have an hardening and a loss of ductility. And the third domain, we have a softening and also a loss of ductility. Then it's not so easy to find a relation with the mechanical behavior and the ductility, which means that we try to analyze first the surface, and we show that without hydrogen, without precipitate, we have a classical behavior, that's like nickel, and all the solute is in solution, and we have a dimper. When we have an increase of the precipitate size without hydrogen, we have intergranular fracture, but with dimper. But when we added hydrogen, it's intergranular fracture, but it's more easy to see that it's similar as a cleavage. But when we zoom, we have a slip line and also a cavity, which is probably a cluster of vacancy. Now you try to check the mechanical behavior. You use a Cox-making model. Do not detail that, but if you follow the evolution of the stress multiplied by the hardening rate, we show this kind of evolution as a function of stress, stage 1, stage 2, and stage 3. And in stage 2, we have a linear slope, and we can define delta 2 and sigma theta 0. And delta 2 is directly linked to the latent hardening, and sigma theta 0 is directly linked to the length path. And you find the results. When we added hydrogen in a CSL, a large fraction of CSL, we have not necessary influence of latent hardening, but when we increase the fraction of random grand boundary, we have a direct link to the increase of the latent hardening and the concentration of hydrogen. It's probably linked to the quaternion atmosphere and the distribution of hydrogen. The second result is the length path. And we show that the length path depends also on the fraction of CSL and the concentration of hydrogen. For precipitate, we have also a dependence of both parameters, and we have not time to explain that because we focus on the fracture. And to question fracture, we use a simple Bérémine model, is issued to the Chebi inclusion model, when we consider the grain as an inclusion on the average medium. And then we identify the critical stress to this equation, is the intergranular fracture stress, as a function of the hydrostatic stress and the equivalent plastic strain, and is dependent of this parameter, which is the strain hardening stage. And we measure that for polycrystalline nickel and a West alloy, and we show that sigma C increase with a fraction of CSL, which means that the intergranular fracture is stress is lower for random than CSL, and it depends on the concentration of hydrogen. And for the precipitate, we have the same results. It means that when you added hydrogen, the sigma C is decreased, and it's surprising that it do not depend on the fraction of the size of the precipitate. So delta C between with and without hydrogen is quite constant, and it depends only to the fraction of CSL in this material. Okay, I can conclude. We do not present that, but we understand we have time to discuss for the conclusion, but we make an intention of the future conference in La Rochelle in the next years, organized by Jama and Sami, two colleagues of our community. And yeah, not only hydrogen in La Rochelle, but it's a nice place, and I invite you to go to visit this place and perform this sport. Thank you.